All right, this is switching now to oceans and ocean currents. Ocean heat. A lot of the heat that, a lot of the extra heat that we've had has been absorbed by the water in the oceans. Recent studies of the energy balance between energy received from the sun and energy radiated back into space have confirmed an extra amount of energy absorbed. This has been largely put into the oceans and not necessarily in the atmosphere, although data is kind of starting to show that the oceans are kind of at max storage and we might start feeling more of an increase in our atmospheric temperature now. Much of this absorbed energy is being stored in the shallow ocean. Warmer ocean water will provide not only more energy, but also increase the amount of water evaporated. Also, CO2 is more easily dissolved in colder waters. As the waters warm, it won't be able to absorb or dissolve as much CO2. Um, okay. Yeah, I guess in the figures. Just showing a lot of running increase, showing that the temperature has been increasing. This is the shallow, whatever it says, what, 2,300 feet deep? And then beneath that, not increasing as much, but still increasing. Thermohaline circulation, thermo meaning heat and haline meaning salt. So ocean currents driven by temperature and salt differences. Um, and wind. Ocean current system transports heat and salinity around the world, could be disrupted by influx of cold, fresh water. And they think this because they think this is what caused the Younger Dryas, which was like this little mini ice age that just happened all of a sudden for apparently no other reason about 13,000 years ago. So people were around for this. So how this works is the cold water sinks because it's heavier than warm water. And they think that that's really kind of what drives it. So it comes up to the poles or down, either way, and it sinks. And then where it warms up, it comes up and then comes back down, sinks, and it's just got this whole little, this is just how it flows. Um, so the thought is if our poles melt, all of us, oh, okay, and I'm going to add, so it sinks because cold water is colder. Also, salty water or cold water is denser. Salty water is also more dense than fresh water because it has more stuff in it. So it weighs more. You can kind of think of it like that. So the thought is that if all of our ice caps melt suddenly, you'd have this huge influx of fresh water at the poles, and the fresh water won't be more dense, so it won't sink. And when if it doesn't sink, it will just kind of stop this entire conveyor belt. And without this conveyor, so this conveyor belt here really does transport and kind of equalize temperatures. It's a one big mixing bowl. If we stopped that mixing bowl, you would find around the equator much higher temperatures and at the poles lower temperatures. Now that doesn't mean that overall, it would still be a warming trend, and eventually the poles would warm up too. But like for that immediate time after the shutdown of this current, it would be much colder at the poles. So Canada and the northern US, Europe would have much worse and longer winters. And then Florida and the equator would be like, burning hot. Um, and so that's a fear. There is a movie about this concept called Day After Tomorrow, which it's a movie, so it like definitely puts everything at the extreme and makes everything happen like instantly. But that is the general thought of that movie if you want to check it out. The Gulf Stream of the Western Atlantic Ocean. You read this Japanese current, Pacific Ocean, global thermohaline, Western Europe would be considered, yeah. Okay. Um, then we have kind of like smaller cycles that change our climate. These can range from, well, this one here says 2 to 7 years, and this is talking about El Nino and La Nina, but there are other ones in other oceans that have different time periods too. But we're looking at like years to decades for all of these. So here's this concept. We're going to start with this concept of upwelling. So there's all this like nutrient rich cold water, and if winds blow the warm water out of the way, all this nutrient-rich water comes up here along the coast down around South America and Mexico. Um, and that's upwelling. And a lot of things depend on upwelling. A lot of critters depend on like these nutrient-rich waters coming up for their food source, as well as other things. So in El Nino, the winds, for whatever reason, I don't think we know yet, stop blowing, or at least they're not blowing as hard. So the warm water gets stuck there and prevents the cold upwelling from happening. Um, and then La Nina is then the opposite when you have, really strong upwelling. Uh, and so they kind of go back and forth. This is a relatively recent discovery, I think. We're talking maybe 30 years ago or so. I think there's a lot we haven't really figured out, like what causes the winds to change, and then how it affects. Like there are these weird correlations to, La Nina year, this part of the country reacts like this, but this other part reacts completely differently, and all these strange correlations. I don't think we really have had enough time to really understand. So with climate change, what else can happen? Besides the changes in ocean circulation, we can have changes in storms, and we already talked about the volume and distribution of glacial ice. Changes in wind and flow patterns and the amount of distribution of precipitation will cause differential impacts. We are getting a lot more rain, and the West is getting a lot less. So we're being flash flooded and flooded like almost constantly now, and the West is almost constantly in a drought. Um, Warming and moisture redistribution also have downsides. It's like it's almost like you want to just take some of our extra water and give it to them, but just how do you do that? Recent evidence in computer modeling indicate changes are already producing more extreme events, and this is those catastrophic flooding, droughts, killer heat waves, hurricanes, tornadoes, thunderstorms. That's another thing. I'm sure you've heard how Tornado Alley is expanding and starting to include us, or at least Western Kentucky, where it used to just be Oklahoma. They still have more tornadoes than we do, but we're starting to kind of catch up. Um, and then with the ocean, so there are correlations between La Nina and extra diseases. And so here you can see where they kind of have diseases. And then here is this. Oh, I put La Nina. It's supposed to be El Nino. El Nino and diseases, El Nino even, and then the amount of diseases go up. I don't really love this graphic here, but whatever. I didn't make it. And then aragonite. So aragonite is a calcium carbonate. And a lot of critters use calcium carbonate to make their shells out of. And as the temperature is warm, then the temperatures are wanting to dissolve all of those things that can dissolve the calcium carbonate. Um, and so we're seeing a decrease in the aragonite saturation, and that's bad because the little critters don't have as much calcium carbonates to make their shells out of. So either they're going to have to evolve into being able to use something else, or they'll go distinct. All right. And actually, I should have put this slide on the next one. So we will next be talking about climates of the past.